Let's talk a little bit about the shapes of molecules. And these shapes are determined by where the atoms and the other electron pairs that might be on an atom are located. What is the angle in between these bonds, or the bond and the lone pair of electrons? So these angles help determine the shapes, and I wanted to review what an angle is. Because in the past I've had assignments where students had to point to the angle and they would just draw an arrow pointing to one atom or pointing to one line. But remember that for an angle you need two lines. It's where two lines meet. So you would need 3 points. So if you only had 2 points and you connected this with a line, you couldn't say that this is an angle because it's not. In order to have an angle, you need a third point, maybe over here. And so these 3 points are connected with 2 lines. And how big this corner is where the 2 lines meet, that is the angle that you're talking about. So when you have a squared off angle, that would be a 90-degree angle. That's if you have a really wide angle. If you want to talk about this angle over here, this would be a 270-degree angle. So a complete circle adds up to 360. Hopefully remember that. So when you're showing an angle, usually you have an arrow pointing to one of the lines and another arrow pointing to the other line, and then you can show the degrees of the angle on that little two-headed curvy arrow that you've drawn. Let's draw another example over here that looks a little bit more like this molecule. So here we have our 3 points, and here we'll go ahead and draw our angle of 120 degrees. That would leave this larger open area as 240 degrees. So in reality, if we wanted to express the shape of this particular molecule in a flat piece of paper, this molecule does happen to be flat, so this works out a little bit more easily. If the center dot were carbon and we had the oxygen, the hydrogen, and the hydrogen, then the angles in between these bonds that carbon has is 120 degrees. These are evenly spaced around the circle. These all add up to 360. So the angle going from hydrogen to carbon to oxygen, this corner is a somewhat open 120-degree angle, wider than 90, narrower than 270 for sure. And the same with this corner over here, it's 120 degrees, and this corner over here is also 120 degrees. So this is what we're talking about when we're talking about the angles and the shape in this molecule. Instead of the 90-degree angle, I wanted to show a 180 degrees. So if you had 3 dots that were in a straight line, so it is not really a corner at all, but it is an angle. It's 180 degrees, the same on this side as on this side. So we do have some molecules that are going to be linear like this. They're going to have their atoms in a line, so I wanted to draw that as well. So how do we decide what the angle of a molecule is going to be and what the shape of a molecule is going to be? What happens is that the electrons that are in the molecule try to get as far apart from each other as possible. So if you were a person, say this dot in the middle, and you were holding on to 2 very powerful magnets in your hands and your arms got tired, then what would happen if these magnets were repelling each other, you would end up with your arms stretched out really far, assuming you could keep holding on to them. But pretty soon your arms would get tired and these magnets would be as far apart as they could possibly be. And so if you are holding onto two magnets, or if an atom is holding onto two regions of electrons that are pushing each other as far apart as they can, then you are going to end up with 180 degrees as your angle. And the shape is going to look like a line. You're going to look linear. Your arms are going to be stretched out in a line with 180 degrees. If you have three magnets, so let's say you strapped one magnet to your knee and then you had two more magnets and they were all repelling each other, then you might end up looking like a Y. Your hands would be up a little bit to get away from your knee, but they'd be stretched out to get away from each other, and you would have 120 degree angles all around you in this shape here. So this one over here, this linear shape, one way to remember it is that it's kind of like a pizza that's been cut in half, the 180 degrees and the linear shape, whereas the one with three electron regions, when you have three magnets, then you're going to end up looking like a pizza cut into thirds with 120 degrees on each side. So we already drew this molecule up above. It looked like this. So it looked like this pizza cut into thirds. These other example molecules, carbon dioxide we drew earlier. So let's go ahead and look at these example molecules. These are both linear molecules. They have this 180 degree angle like a pizza cut in half. In each of these cases, the carbon is holding these two regions of electrons as far apart as possible. So even though this carbon has 4 bonds, which carbon tends to have, 4 bonds, it still is just 2 electron regions, because these bonds cannot separate and be further apart because they're both leading to the same oxygen. So these bonds have to be pointing in the same direction. So this counts as one group of electrons that has to point in a certain direction. This double bond is a second group of electrons that is pointing in the opposite direction. So even though carbon has 4 bonds here, it only has 2 electron regions. So how do we count the electron regions? We're going to count how many bonded atoms, not the number of bonds, because if you have a double bond or a triple bond, that has to all point in one direction. So instead of counting the number of bonds, you count this oxygen once, because all these electrons have to point in the same direction. So you count this atom and this atom. We have 2 bonded atoms on the carbon, and we have 0 lone pairs on the carbon. If the atom has lone pairs, it has to make room for those as well, but this carbon does not have lone pairs. This carbon is in the same situation. It has 2 bonded atoms. So this carbon is bonding to this carbon, and it's bonding to this hydrogen. This carbon is not directly bonded to this other hydrogen. It does not have electrons leading to this other hydrogen that it has to make room for. So we're not counting that one. We're counting this carbon and this hydrogen. So carbon has 2 bonded atoms and again 0 lone pairs. So this carbon is also linear. If you look at this carbon is also linear. It has 2 atoms and 0 lone pairs. So since this carbon and this carbon are both linear, the entire molecule ends up being linear. So for this molecule over here, to determine the shape of the molecule, we're really looking at the center atom. We could determine the geometry of this oxygen and where these pairs are located on the oxygen, but that doesn't affect the overall shape of the molecule too much. So we're looking at the central atom, this carbon. And this carbon is bonded to 1, 2, 3 atoms, and it has 0 lone pairs. And so altogether, the 3 atoms plus the 0 lone pairs add up to 3. So that's how we're getting the electron regions. We're adding the bonded atoms plus the lone pairs. So we have 2 plus 0 equaling 2. 3 plus 0 equaling 3. And that gives us 120 degrees and a trigonal planar shape, which is a flat object being cut into thirds, so like a pizza cut into thirds. There's another way that we can get 3 electron regions. Instead of having 3 atoms and 0 lone pairs, we could have 2 atoms and 1 lone pair. That would still have a 120-degree angle, and the geometry of the electrons would be trigonal planar. However, we have a different shape of the molecule. We have a bent molecule even though the electron geometry is trigonal planar. This will happen when you have one of your electron regions being a lone pair, because the lone pair of electrons is so tiny that it doesn't really show up in the shape. It doesn't look like much, and so instead of looking like a pizza cut into thirds, this is going to look bent. So let's take a look at this SO2 molecule. We still have this pizza cut into thirds as the electron geometry. So these electrons in the lone pair are separated far away from this double bond and this double bond. So this is like a pizza cut into thirds, just like this molecule was. But the shape, if you look at this shape, it just kind of looks like this. There's not this third atom over here. So it just looks like a bent line. It doesn't look like the other molecule, which looked more like a pizza cut into thirds. So it just looks like this bent boomerang shape. That's why we have a different name for the shape. This happens over here as well. Whenever you have one of your electron regions being a lone pair, then the shape will have a different name from the electron geometry. If everything is an atom, then the name of the electron geometry and the name of the shape will be the same. But when you have some lone pairs, that's when you have a new name for the shape, because it just looks a little bit different than having something where all of the regions are atoms. So next we're going to look at some ways to have 4 electron regions. You can have them with 4 atoms and 0 lone pairs. You can have it with 3 atoms and 1 lone pair, or you can have it with 2 atoms and 2 lone pairs. Now you'll notice that we do not have a 90-degree angle. We do not have a pizza cut into 4 pieces like you might expect if you were following the pattern. We had a pizza cut in half, a pizza cut in thirds. Why not a pizza cut in fourths? That would give us an angle of 90 degrees, but there's no reason why the molecule has to be flat. We can use all 3 dimensions, and if we use all 3 dimensions, we can spread apart a little further than 90. So over here where I'm drawing you with your magnets, here's you. You have your 2 arms up with the powerful magnets, and now you have another powerful magnet strapped to each one of your legs. And so to maximize the space, instead of standing straight up and down, you might put one leg forward and the other leg backward. We'll draw this forward leg really thick, like you have bell bottoms on or something. Okay, so we have this magnet forward and this backwards. So you're standing with 1 foot forward and 1 foot backward, and then your arms are out to the side. So I'm trying to show 3 dimensions here, but that is how you get a 109.5 angle. I'm running out of space to draw the tetrahedron and the pyramid and the bent, so I might take a little break and show you the online simulator to look at these shapes, and then maybe come back and draw them down below. In a live class, we would bring some models to class and play around with them to investigate shape, but this online class we have in Module 4 a Fun with Molecule Shape and Polarity page where I give a link to some simulators. So the first one has to do with molecule shapes. Let's go ahead and check the boxes where we can see both the molecule geometry and the electron geometry. And let's check showing the bond angles as well. So here we have a central atom that is holding on to 2 things, 2 atoms, and so it is a linear molecule. This one kind of looks like the carbon dioxide molecule that we were looking at, the carbon with two double bonds, two sets of double bonds. And here is the other linear molecule we looked at, the carbon that had a single bond to hydrogen and a triple bond to the other carbon, which then had another hydrogen. So we had a large linear molecule there as well. So here is a molecule with three things attached. It's kind of a flat shape. You can see that. And the angles are 120 degrees, a trigonal planar shape. This one is more like the BF3, where the boron had 3 single bonds to 3 fluorine atoms. And this one is more like the formaldehyde, the carbon with the oxygen double bond and the hydrogens single bonded. But again, these are trigonal planar shapes with 120 degrees. The SO2 molecule was more like this. The sulfur had a double bond to oxygen and a double bond to oxygen and a lone pair. And so the electron geometry is still trigonal planar. It still has that 120 degrees, but the molecule geometry is bent, because if you remember that you can't see electrons, they're kind of invisible, then it would just look like this bent shape. Let's go ahead and make this CH4, the carbon with 4 single bonds to 4 hydrogen atoms. So this is not a flat pizza cut into quarters. This is a 3-dimensional shape that sort of looks like a tetrahedron here. So here we have the carbon with a hydrogen and another hydrogen in the screen, one going back into the screen and one coming out at you from the screen. There's no lone pair, so the electron geometry and the molecule geometry are the same. Then for the NH3 molecule, instead of a 4th atom, it only has 3 atoms, but 1 lone pair. And so we still have that 109.5 degree angle. This is not the flat molecule that the BF3 was. So if you get rid of the lone pair, it's flat. But because there's a lone pair, it's now not flat. These hydrogens are sort of bent away from being in a flat plane. So this would be a trigonal pyramidal shape, although still the electron geometry is tetrahedral with the 109.5 degree separation. Now let's do water with 2 atoms and 2 lone pairs. It still has that tetrahedral electron geometry with the 109.5 degree angle, but the shape just looks bent, especially if we get rid of those lone pairs. It just looks like a bent boomerang shape. So this is pretty fun to play around with, make models of the different molecules and figure out what their shapes are, and sort of see it in three dimensions just because of the movement. I mean, it is a flat screen, but it looks a little bit more real than my drawings probably. All right, let's see if we can just draw these 3 molecules on a flat paper. All right, what we're trying to show here is these 4 hydrogens in 3 dimensions around the carbon. And so these ones with regular lines are in the plane of the paper. This hydrogen with a wedge is sort of coming out of the paper towards you or coming out of the screen. The one with the dotted line is going back into the screen away from you. And so if you just look flat, it looks obviously like these 2 hydrogens are further apart than these 2 hydrogens, the way they're drawn on flat paper, but it's meant for all of these angles to be equivalent, 109.5, like it looked in the simulator. All right, for this ammonia molecule with NH3, the nitrogen is making room for 4 things, the 3 hydrogens and the lone pair. So it's not like a flat pizza cut into thirds where all of the hydrogens are in the plane. The existence of this lone pair of electrons pushes these 3 bonds a little bit down away from itself. And so these are no longer flat. we have the lone pair and the hydrogen kind of in the plane of the screen, this hydrogen going back into the screen, and this hydrogen coming out. And so all of these are slightly bent downwards away from that lone pair. So the angles are 109.5, just like they are for the tetrahedral CH4 molecule, but instead of looking like a full tetrahedron, since this lone pair is here, it has more of a squat, shorter, flatter shape, and so it looks more like a pyramid, and that's why the shape is called a pyramidal shape. We can also call this trigonal pyramidal. In 101, we learn another shape that has the word pyramidal in it, so we'll specify that this is trigonal pyramidal. This over here also has 109.5 degrees angles, a water molecule. Because the hydrogens are not the only thing the oxygen has to hold on to or make space for. That's why the water molecule is not linear, like you might think when you just look at the formula. You might think, oh, the oxygen has a hydrogen on one side and a hydrogen directly on the other, but that's not the case. The oxygen also has these two lone pairs, and so it does have four things, two atoms and two lone pairs. And so instead of linear, it has more of a bent shape. The electrons have a tetrahedral geometry, but the shape of the molecule overall just looks like a bent boomerang here.